This is the solution video for question 10 from section B of the fourth sample test for the CSAT paper. In this question, we're given two tins, both containing N biscuits. We randomly choose a tin and a biscuit is removed. We then repeat this process, removing biscuits from randomly chosen tins until the most important thing with this question is to get a clear picture of what's going on and have an effective way to notate things and to visualise and see what's happening. So we're going to notate possible outcomes like this. So we could have this, say, which means we pick A from 1 from our first time, and then when we come back we pick A again, then we pick tin B, tin B, tin B, tin A, etc. And then our final A means that we picked the last biscuit from A and we're done. And there's clearly some biscuits still in B, or we would have ended earlier. So these sequences can be different lengths depending on, say, if we happen to pick all the biscuits from A first, or if we mix it up and when we end there's only one biscuit left in the other tin when we pick A. Here's another sequence we could have. So pick B, tin B, tin B, tin B, tin A, etc. And then end when we pick the last biscuit from tin B, but there will still be some biscuits in tin A. And we know we choose our A or Bs with probability half, because we randomly choose a tin, irrespective of how many biscuits are in it, until we choose our nth A or our nth B. So this A will be the nth A in the sequence, and then we stop. And similarly, this B with the nth B in the sequence, and then we've stopped. So we're asked to find the probability that there are K biscuits left in one of the tins when the other becomes empty. This is awkward to deal with, so we're going to look at a simpler thing to work out. We're going to look at the probability that there's K biscuits left in B when we end. And once we get this answer, if we double it, because the reverse could happen, it could be K biscuits left in A when we finish in B, and clearly because K is bigger than 0, both events can't happen. So if we work out this, we'll find our answer. So now we need to suss out what happens in the sequence when this happens. What are sufficient and necessary conditions for this string of A's and B's to mean that in real life we've got K biscuits left in tin B. So for K biscuits left in tin B, we need the sequence to be 2n minus K length. This has to happen because that means when we finish, there's K biscuits left in one of those tins. But we need to make sure that tin is B, not A. So what we need is the last term needs to be A of the sequence, because that means we've took the last biscuit out of A, so we know there's no more biscuits in A, and we know there's K biscuits left generally in some of the tins, so there must be K biscuits left in B when we're finished, which is what we want. Now we can reformulate these, because this is quite hard to work out. So another way to say this is come up with events C and D. Event C is that we pick n-1 A's in the first 2n minus K minus 1 selection of tins. So when we pick A or pick B, we need to pick n-1 A's, because that means when we make our 2n minus K selection, there'll still be biscuits in A and B, and there'll be exactly one biscuit left in A that we then have to pick. So if C and then D occur, we know that's exactly when there will be K biscuits left in B. So now what we need to do is we need to find the probability of C and D both occurring, namely the probability of C intersect D. So how do we find this? Well, we know the probability of C intersect D is the same as the probability of C times the probability of D given C, and this is much easier to work with. So we'll start with a nice one first. We'll look at the probability of D given C. And we know this is equal to a half. Now, why is that? Well, what we know is if C occurs, we've got our sequence going along, and we know there is one biscuit left in A, and we know there's some biscuits left in B. And so when there's biscuits left in both tins, we know we pick A or B arbitrarily with probability of half. So probability of D given C, i.e. selecting A on that 2n minus k selection, is a half. So we know this. Now, probability of C. How could we work out this? Well, C should probably make you think of someone you've seen before. And that is, it's a lot like choosing, it's like a binomial, right? We've basically got 2n minus k minus 1 trials, and we need n minus 1 successes, i.e. exactly n minus 1 times we pick A. So we know the probability of C is this, because the probability we pick A is a half, so P is a half and 1 minus P is a half. So we get a half to the 2n minus k minus 1, and then we've chosen n minus 1 successes from 2n minus k minus 1 selections, and so 2n minus k minus 1 choose n minus 1. So we get this by considering C as an event in a binomial distribution. Now we simply need to times them together. So it's easy, we just combine these powers, so we get probability of C intersect D is equal to a half times 2n minus k times 2n minus k minus 1, choose n minus 1. But remember, that's not our answer, because this was the probability k biscuits left in B. We could also have the event occur of k biscuits being left in A, and that would completely satisfy this. And clearly the probability of k biscuits left in A is exactly the same as the probability of k biscuits left in B, so we need to double this. So we've done that just by decreasing this power by 1. And our required probability is a half to the 2n minus k minus 1 times 2n minus k minus 1, choose n minus 1.